So this grouping you see is one you're going to see a lot. This number 68% or something around there, you'll see very often. This thing of like how many standard deviations from the mean, this is going to become a really significant thing that you'll see often. In fact, this is not usually how courses are done now in university, but it used to be that every test you would take in university would be grouped by this distribution, regardless of how people actually scored. They would say, we're going to put that on the curve, or we're going to curve that class. That's talking about this distribution. So take a look here. In lots of measurements, like length, volume, mass, they often end up grouped kind of similarly around them. Taking a look here, weight of infants, time taken to complete an assignment, or maybe in this class not complete an assignment, height of students. Well, if we were just to connect the top points, what do these look like? Just like connecting the dots. Maybe a little smoother. Or similar on the next one. You can kind of see, this is what we would call a bell. Right? It's a curve that looks sort of like a bell.
Yes.
And if data makes up a curve that looks like a bell, we would call it a normal distribution, or data that is distributed normally. Now, this bell curve, this normal distribution, however we want to talk about this is like a really common data thing we'll see. So the way this is set up is like how many times it happens, and then the amount of data values. And this is very predictive in statistics. Oftentimes we'll find that things are normally distributed about some curve, about some mean, and we can make some predictions based on how much stuff is, say, this close to the middle, or how much stuff we should expect to be, say, this close to the middle, or whatnot. And that stuff we talked about yesterday, standard deviations. A standard deviation is just talking about how far some amount of data points are from this mean. So we're saying, okay, how many things are one standard deviation within the, above the mean, or how many data points would be up to a certain point, or something like that. And we should be able to predict that with the bell curve. So we'll talk about that. So first of all, let's use a concrete example. So there's a manufacturer making 100-watt light bulbs for this company, and they want to figure out how long their light bulbs last. Now, they test 44 bulbs, calculate the mean to be about 900 hours, standard deviation is about 50 hours. Here's the lifetime in hours. So first of all, let's look. Does this data match the histogram? What's the lowest one here? Lowest one here. Right. And it looks like there's just one in that group. This is a histogram, so it's saying, okay, within the 750 to 800 range, just the one. Within the 800 to 850 range, 1, 2, 3, 4, 5, 6. Okay, cool. Within the 850 to 900, 15 to 900. Right. So it's just showing groups. Yep.
After the 700, what is that like line?
Oh, that's showing that this is a cutoff graph. So we've talked probably in your earlier math courses about how you can make data kind of misleading, and one way often is to not start from zero. Now on the x-axis that's less true, because like when talking about time, 0 is always an arbitrary reference point. But if you see this on a line or this here, it's just saying this is cut off, and we're skipping this part of the graph. So really, it's saying this graph actually goes all the way over behind my desk. It's just there's nothing included on it. So now we're starting from 700. Okay? So it's basically saying this is a cutoff graph. And you see, like, so this was the only one in this range. All of these ones here were in this range, and on and on and on. So a histogram is saying which pieces are within which grouping. That's a nice way of kind of using the approximate length or something, right? Did it matter really whether the life of a bulb was 830 versus 845 in terms of the scope of this study? No, they're within the same range. It's about the same lifespan, right? And you can see there's also one high outlier, 1049. It almost snuck into this next category, which is interesting. Okay, so now let's use this histogram to complete the following table. How many bulbs we're under 800. Okay. 8 to 850, I already mentioned this one.
6.
Yeah. Now, what about this next one? 850 to 950. Okay, and then it looks like this one was like perfectly mirrored going down. That's almost too good.
Whoa.
So then the percentage. So how do we find the percentage of bulbs? Well, we take the 15 out of the total 54, divide it. You see that what's happening here? 15 out of 44 is 34%. Okay, how about 6 out of 44?
14%.
Thank you.
How would you?
Pardon?
You're thinking. Not comfortable with.
Why did you guys make that happen?
Not bad.
Where did you do that?
14% here. And then how about 1 out of 44? 2%. Okay. That's pretty nice. 2, 14, 34, 34, 14, 2. And just a kind of heads up, often when we're looking at data like this, we'll start thinking about like, okay, what would be in these 2 groups? Or what would be in these 4 groups? Or how would we group these within a certain amount of groups? Or which percent would be below? So if mu is 900, standard deviation is 50, let's think about this in terms of mu and sigma. So the first one, mu is 900 and sigma is 50, then this is equal to mu plus sigma, right? This is 1 standard deviation. The 850 then would be mu minus sigma. This is 1 sigma under the mean. Okay, 800. How did you get there using how many sigma?
So for mu, is it just like a squiggly M? Or?
It's an M with like a tail in front. That's actually why I have this up here, right? So in general, with these, we're talking about lowercase Greek letters, but mu is like mu with a little tail. Rubber tail, a mustache.
And sigma's like a sideways M.
Well, no, but lowercase sigma. Lowercase sigma, the circle with the little.
Yes, I just have a question.
Yeah,
Is lambda the only intrinsic, or are we going to use it too?
we won't use it in this.
Oh.
No, it won't be a letter used in this course, but it definitely is.
Yeah, I used it.
Alpha.
I'll tell you. But in stats, what we're talking about right now is the key steps. Yeah.
How come, like, out of those, like, out of all the letters, so we got, we chose sigma and mu, and not like epsilon?
Outstanding question. Take it up with math.
You don't know? I thought you said you loved math.
I love math. No idea.
Yeah.
In general, the reason why is going to be because of like the name that the thing was talking about in a certain language. Like sum is kind of obvious. You can see why we use capital sigma to talk about the sum of something.
Yeah.
We use lowercase sigma to talk about the lowercase something, and that's clearly mathematicians deciding, okay, it starts with an S, we're going to use a Greek letter, which Greek letter makes a sound, sigma, so we'll use that Greek letter. But I have no idea why mu is used for, I guess mu would be because that makes the M sound, but I don't know why mu is like the friction coefficient in physics. I have no idea why. Right, so some of those. Anyways, okay, 800. How is 800 related? How many standard deviations is 800 away from the mean? 2. So how can we express that? Yeah, mu minus 2 sigma. Good. And how about 1050?
2 plus
Great job. So now if we were labeling this normal distribution curve with 900 as the mean, and every standard deviation is 50, let's label this. Okay, so this was 850, which is mu minus sigma. 1,000, 1050, 800, 750. Yeah, I have to know, what does mu mean in popular vernacular? I think I now sort of half understand what sigma, alpha, and beta. What about mu? Is this something that
Well, that's when you,
Be quiet and you're just, that's basically what it is. Be quiet.
no,
It's
no,
not
no,
like
no,
be
no,
quiet.
No, it's not.
You know, usually when you put the tongue in the top.
Kinda like I'm better.
it's in order to get a better job? Okay. It's saying I'm dominant over you or something.
No, it's
That's fine.
Oh, okay.
That's fine.
I tell you guys, I appreciate people trying to explain viral trends. It is, it shows how silly sometimes they are, but I now know that I'm supposed to do this while he's not.
It's not function.
Okay, so I've learned, I don't want to be a mouth breather. Okay, no, it's wrong. Okay, and we'll finish with how many sigmas and mu's we are from the mean. So this is mu plus 2 sigmas. This is mu plus 3 sigmas. This is just mu. This is our mean. Minus. So right now we're just setting up a curve showing the data we use. So this is still based on the last page. Yep.
For like a go,
Yeah.
would it just continue to keep going, or would it eventually hit 0?
Great question. Great question. Depends how big the data set is.
Okay.
In theory, technically, if it's a horizontal asymptote, it'll never touch the. It'll never touch. But if we're talking about real data, of course, there's a spot where it's not. Right? In terms of like our example here, light bulbs. Were there any light bulbs that didn't last? Like that lasted 300 hours? No, everything lasted more. Right? So in that case, there was nothing in that category.
So nothing will ever hit 0. So it'll get low, but it'll never hit 0.
Oh, but in this case, it did. There was nothing. But in theory. But yes, if you go enough standard deviations away from it, you should expect nothing.
Why don't some do I hear that?
All right, now let's try to figure out what our percentage is going here. So what was the percentage in the mu minus
Sigma.
in the mu minus sigma categories and the mu minus 2 sigma? What was the percentage there? 14. What about the one above here? What about mu plus sigmas and mu plus 2 sigma? Right? And then what about in the lower categories? What in the plus 2%? 2%?
Is this the same one over
Now, we've actually done some fairly significant rounding here. Did anyone keep the actual data numbers here? Because we're making some rounding moves where if you go 34 plus 34, 68, plus 14 plus 14, what's 28 plus 68?
96.
And then plus 2 plus 2, so that's 100%. And you see there's still information beyond there, so by rounding up, we've actually removed the extra stuff up here and the extra stuff down there, which a tiny percentage is, right? So by rounding, we've kind of cut that out. And you will see a little bit more precision as we get into the other ones.
So those don't exist for this one.
Well, yeah, exactly. There was nothing there in this case. Now, this is a little bit more precise on what we would call a standard distribution graph. So here's a normal distribution curve. It has a mean value of 0, standard deviation of 1. Each step is moving 1 on the x-axis, or each standard deviation is 1 on the x-axis. You can, if you'd like, and I would like you to graph y equals 1 over square root of 2 pi times e to the negative 1/2 x squared.
I hate that.
No, you have to switch to. I think it's for math and it's like yeah, exactly. 1.7.
I don't know.
Okay, this is dead now.
Yeah.
Grab a calculator. Try to graph this thing. What? Nope. You're using X already.
Is that E with power?
Yep. E to the power of negative 1/2.
Malcolm back.
Divided by square root of 2
You have the way you find E on here. E is second ln or second ln. It says e to the x, so you'll put e to the x and then you'll put in the negative 1/2 x squared as the variable. So maybe I'll just show you. Pardon me? Yeah, totally. Exactly. 5.
Oh my goodness. You say all the time that I make her saying it.
Yeah, your guys looks like this when you grab with that. When you're grabbing it, right? Turn or something like that.
Oh shit! Wow!
Whoa.
I did it! I did it!
My whole conversation in the bullet.
Oh my God.
Not catch anything.
Catherine won't get five.
I was doing this to you. You didn't see shit. Yes, you were.
And notice the window settings, it wants a really, really low window setting, because recognize the top here is 1, so we don't have to go close to as high as it starts with. So -4 up to 4, down to 1, negative 0.1, 0.5, and my 1s. So my graph looks something like this.
I did it all right.
Okay, now,
Yeah, I got it.
nice. The general reason why we're doing this, just to have a reference point of what this looks like. We can do most of this though with what we have in our book. So let's go back into our book. I'm taking a long time here. Sorry, guys.
No, I did not. Who you lying to? It's a lie, bro.
Liar's gonna lie, right?
Yeah. Lying is a lie.
Now, here is a standard normal distribution curve. You see that our numbers were very close, but we made some rounding errors because we were talking with a data set of 44%. I mean, 44 people. But in general, about 34% are within 1 standard deviation on either side. So about 68% are within 1 standard deviation of the mean. Then you add in, and you see, by the way, where we rounded these to 14, 13.6 leaves a little bit less than that, right? We're adding an extra 0.4 on each side. But so we have an extra almost 14% between 1 standard deviation and 2 standard deviations on both sides. So just from looking at this initially, how much of the curve is within 2 standard deviations of the mean? How much of the curve is within this chunk?
I feel like I zoned out.
How much?
95%.
Yeah, about 95%, right?
You just like add all of that together.
Yeah, exactly. Just add up all those percents.
Yeah.
Okay, and now, how about this? On this standard distribution, the normal distribution curve, how much information is within 3 standard deviations?
Three standard questions.
How much is from mu minus 3 sigma to mu plus 3 sigma? Right, and if you look at this, about 0.1% and about 0.1% on each above there. So yeah, that makes sense. Almost everything is within 3 standard deviations, but not quite.
99%.
And when you talk about outliers, this is a term that gets used sometimes in all sorts of contexts. Outliers are talking about stuff out here, right? So yesterday we were talking about Ahmed's scores in our Math 20-1 class versus everyone else. And you know, he in our setting yesterday was somewhere up here, right? So Mr. 100% when the rest of us are over here. If the average is like 45 or something like that, and he's scoring up at 100, well, that's clearly on the edge of this curve, right? On the edge of this distribution. And actually, you'll hear, still people in engineering will talk about bell curves often because lots of engineering courses are still just marked on the curve. So it'll be kind of grumpy if like the whole class gets 50 or 60 on an exam, but there's two people that really crush it. It's like, oh no, you pulled the whole curve up. The rest of us are all similar, and you guys ruined it for the rest of us, right? You did too well. You'll hear people talk like that on curves because how the data is distributed makes a huge difference on their mark. I had a university course. This is quite a while ago, maybe a year or two back. About back when you guys were not born. But it was this course, it was called an elementary theory of interest. It was extremely easy. It was no longer offered after that year, in fact. And in this course, it was basically just like a whole bunch of interest calculations. But I one day looked around the class, and I counted 18 people in the lecture hall. And our class had 120 students. So clearly, no one thought it was too important to go to, which is not common in university lectures. Usually people go, but this was it was quite easy. Anyhow, I was going into the final with 100%, and I think I aced the final. Maybe I got a question wrong, and I didn't get an A+. So I was thinking about this, and that told me that this course had an average that was so high that in order to get the A+ or whatever, you had to literally not get anything wrong all year, because if it's up here and the average is like here, well, then suddenly everything is included with it. And the way that university grades were working in that case was like, whatever, 68% gets a B or whatever the number was, and then like this percentage gets a A-, this percentage gets a, and like smaller and smaller percentages. So when you hear about courses being marked on the curve, they're saying there's some number, usually in first year courses B-, second year courses B, whatever, that's your mean. And then they're just saying if you're this much away from that average mark, you're, within this group. B-, C+, C, however it goes, but it'll just be moved like this.
So it's based off how well the class is.
Yes. So if you're in a curved class, that's what's happening. So that's why you'll hear people talking about, oh, was it on the curve, those kind of things. And the expression that you used to hear was, oh, I'm just riding the curve, almost like, oh, I'm just surfing in this middle point of the curve, because it's like, oh, I'm somewhere in that middle group. Doesn't really matter how I do, as long as I'm within that middle group. Right, so and that's part of why obviously the curve is less often. But it is a good way of comparing a group within each other. Okay, I'm really going on a lot of tangents. Sorry. I hope you'll
not even on the mountain at that point.
Yeah, that's exactly right. We're on some other mountain. In general, okay, here are some main properties. If you've been zoned out while I've been rambling through it, journeys in meadows and pastures, come back now. We're going to talk about mountains. So, area under the curve is 1. So all of this stuff adds up to 1 or 100%. Alright, so we're talking about all of this is within 100%. So like this section here is 0.68,
Is it 1 or 100%?
the same thing. 100% is 1% means out of 100. So 100 out of 100 is 1.
Oh,
Normal curve extends infinitely left and right. I asked a question earlier. So the curve itself extends infinitely, doesn't actually reach the horizontal axis. There's not a cutoff point, but practically there is. Right? Practically there's well,
but it would just get smaller and smaller.
Exactly. Infinitesimally smaller. Normal curve is symmetrical about the mean, which means that whatever your mean is, there's the same amount of stuff to the left and to the right. And by definition, that better be how your mean works. Data is represented by the area under the curve. And on a normal distribution, mean, median, mode are the same. Okay, so when you curve something, mean, median, mode are the same. Well, let's think about this. So by the way we've set this up, by the way we've set this information up, what's the most common value?
The middle.
0.
And what's the middle if it's symmetrical?
0.
And what's the average if it's symmetrical? Because of how so, exactly. Based on our definition we used, yes. Lacey T, do you guys need to explain that?
I was trying to.
True. But you know what? I'm not going to complain. We're going to interact.
Yeah. JJ's listed with the needs and that, right? Yeah.
I'm confident, based on his sterling work ethic habits, and he'll get 5 minutes. Right, Paul? So, nurse records the number of hours an infant sleeps during a day. Then records the data on a normal distribution. Values shown differ by 1 standard deviation, so each of these is 1 standard deviation in width. So what is the mean and standard deviation here?
Mean is well, the standard deviation is 2.
Awesome. Okay. What are A, B, C, and D then?
6, 8, 16, 18.
Good, we can count by 2. What's that? And what percentage of days to the nearest 100 does the infant sleep? Between, say, 12 to 14. Let's just go back a second. We're taking a look at these categories. So what percentage is he in this 0 to 1 category is first of all being asked?
34.
To the nearest 100.
0.019.
Well, going on the wrong side of the room.
Average.
This is dead.
Okay, how about between 8? How about between 8 to 16?
95.
Nearest 100. So we're thinking how would we I track what you're doing, but let's be really precise here. So we have 34.13 twice, right? And we have 13.59 twice. There's two of these, so that's 16.26 and 27.18. Yeah. So total. Does it make me flounder up here?
Oh, nice. 6,000.
95.1.
24.
We have less
Okay,
than 6.
less than 6 hours, so less than A.
Uh-oh.
How would we figure out this? Hint, hint. Go back up here and look at it. No, it's 0 points.
0, 0, 13.
Well, it's just 0.13%, right?
Oh, right, never mind.
But you're right to recognize if we're talking about out of 100 days, this infant sleeps 0.13 out of 100, right? They sleep less than 6 hours, 13 out of 10,000 days.
That's a lot of things.
And
That's not very high.
how would that be for a year?
I think it's for.
It'd probably be like 1 day.
Yeah, I guess it was 1 day in this case.
Like, what would you?
One day.
Now, based on what we have here, why can't we figure out how many days they sleep less than 13 hours? Right, if we were trying to figure out everything there,
Right.
why can't we find that yet? We will be able to, don't worry. No fear, you will get this superpower. You just don't have it yet. Right now we're only talking about full standard deviations. 13 is equal to mu plus a half of a standard deviation, which so far we only know how the curve is broken up per full standard deviations. Right, so we can figure out based on full European standard deviations, but this is halfway, it's in between. We don't have that power yet.
But it's right there.
Where?
It's there. Right there.
Where?
It's,
But the thing is this, I don't know. Like, I see what you're saying. You're thinking, oh, then just cut this group in half. Look at this. is this split evenly in half?
No, not at all.
Right, no, so there's more in this chunk than there is in this chunk. That's actually one of the key parts of a standard
No,
deviation.
you do it right now.
Every chunk, no matter how small you slice them, the closer you are to the mean, those chunks are bigger.
There is a way to
Are
cut
the
it
chunks
perfectly
the
in
same
half.
width?
That's true.
The chunks are always the same width, right?
What?
The chunks are always the same width, right? Like-
Well, yeah, but what the thing we're recognizing right now is, so yes, right now the chunks are all in one standard deviation. But what if we were breaking into smaller chunks? How would we figure that out? And then that's what we need to use what we call z-scores. That's talking about basically parts of standard deviation with reference in terms of standard deviation. Which, by the way, right here,
Oh, no.
we have our z-score charts. So this will be a power you can do. Yay! Also, I think it's in the back of your book. Cover your book. Yes, no, maybe so.
Why is that
Yes,
someone
it
telling me
is.
that?
Damn. Yes, it is.
What the heck?
So, it's not possible. What? Good morning. Nice to see you. Welcome back to Planet Living. Not possible to determine the percentage of the days the infant sleeps less than 13 hours because the curve is only talking about full standard deviation. Z-scores can be used to determine these percentages. So in this case, normal curve, data value of 18 was how many standard deviations above the mean?
What's the supposed when you say something?
Was how many standard deviations above the mean? 18.
18.
Was 3 full standard deviations above the mean? So it has a Z-score of... A Z-score is just saying how many standard deviations it is above the mean, plus or minus. How would data value be? It's 2 standard deviations below the mean, so it has a Z-score of -2.
I feel like,
Sorry, this is what we're talking about. Rewind. Z-score for a particular value is how many standard deviations above or below the mean. We're just talking about the information on the last page. Still what's in chart. So we're talking about 12 is the mean, standard deviation of 2. So like 12 plus 2 plus 2 plus 2. 3 standard deviations gives us 18. 12 minus 2 minus 2. 2 standard deviations below the mean. I see that everyone loves the stats name so much. Great.
We love stuff.
Stats love you. Okay, how about data value of 12? How many standard deviations is that above 12? Oh, good job. So Z-score?
0.
No, it's 0.
God, I get it now.
Positive or negative 0?
There's no negative, zero.
No.
That is the middle point between positive and negative. It's not positive and negative. Okay, 13. Oh.
0.5.
Okay. It's 0.5 standard deviations above,
Wait, what?
Is that
and has a Z-score of
13?
How do you figure this out?
I recognize standard deviations are 2 in this case. So 13 is half of 2 above 12.
Somebody's calling me from Wood Buffalo.
That's the largest municipality in Canada.
Hey, just stop getting scam calls. That's my scam calls now. Like, I don't want to get scam.
Nope, definitely not good conversation. Although it is wrong. I like that.
I miss scam calls. Every time I accept a scam call, they just hang out.
Yeah, don't ask me.
That's a really bad way to scare me.
We are really tailing off here, guys.
So sorry.
Why don't we try to crush through this? I see that Z-scores are beginning to baffle us. Start with this. Z-scores are just standard deviations, but in reference to 0 as the mean. So in the last graph, we talked about a mean of 12. And 14 was 1 standard deviation of 2 above the mean. And 16 was 2 standard deviations of 2 above 12.
I feel like you're speaking a different language.
And if instead,
Explain this whole different.
so in this situation where 12 is our mean,
Yes.
and each of these sigmas is 2. So then we're like 10, 8, 6, going on and on.
Yes.
14, 16, 18. So now if we're doing Z-scores, we're talking about Z-scores. Do I need that? I better not see that phone up. You're in an Alberta school right now where the law is that you don't bring your phone to class. Stop doing that. So, if we're talking about this now in terms of Z scores, oh, this is great. I have a bunch of blue markers. Let's label this instead in relation Z scores each one. So what's the Z score 12? Nice. Oh, this is great. I'm glad I picked up sheet. Wait for the black one. Thanks. And what's the Z score 14? What's the Z score 16? We were talking about how many standard deviations. Oh. 3, -1, -2, -3. So now we can see how, okay, 13, this point here, that's 0.5 Z score. It's halfway between the standard deviations.
Okay.
Okay, we're sort of half track. At least our brain is not currently exploding, so that's good.
Okay, so.
And so now it's really nice that I literally did this.
So if you think about it, it's like each of them add up to 2 usually, but then it's kind of like instead of 1, 2, 3, 1, 2, 3, instead of 2, 2, 2, 3.
Yeah.
Okay.
So as we look at this, mu plus sigma, mu plus 2 sigma, so the Z score is basically how many sigmas you added.
Okay.
It's like a timeline. And in the middle is 0.
Yep, exactly.
Yeah.
I love it. Brilliant. Here is the center of your life. Yay. It's grade 11, the high point of your entire life. Good job. And, now we're just downhill from here. Okay, that's not how it works. I tried to go with the analogy. It was a bad one. It was a bad one. So to figure out the Z score of the data of 13, well, we think, okay, we're going mu plus however many sigmas, right? The Z score is however many sigmas. Yeah, so 0.5 sigmas, 12 plus 0.5 By the way, have you ever heard the expression, it's all Greek to me? At least in this case, we are literally using Greek letters. But yes, it is all Greek letters, literally, to express this nice and simple mathematical concept. Excellent. Matter of fact. Because each sigma was worth 2, right? Our standard deviation in this situation was 1. Right? Every standard deviation was 2 here, and our mean was 12.
Okay. That's the same for you.
No, the standard deviation was defined. That's what we were doing yesterday, was finding our standard deviation. Yes, our standard deviation is 2. Now, we're getting it, guys. We're getting there. Amazing. So Z score. And this is actually all this table is telling you. Z score is, to find your Z score, take X as some particular data value, whatever data value you're wondering. In that case, it was 13. Right? 13 in this case, minus the mean, which is 12. And divide that by your standard deviation, which in this case was 2. Right? Yeah.
13 minus what?
So in this case, the way we found that Z score we were wondering about was, we went 13 minus 12 divided by 2. And yes, 1 divided by 2 does happen to be a half. So our Z score was a half. Yep.
Is that or are we actually?
It's actually Z.
So-
Wait, this is the worst part of stats, is you have English letters and Greek letters, and sometimes your example something you use. And then if you want to continue stats, you're going to calculate tables and Z tables, and then you'll get random Greek symbol squared table, pi squared table. So yeah, that's fine.
Why not the whole thing?
Alright, so here's what we see. This is all still talk the same stuff. So within three sigmas of the mean, or within 3 Z scores of the mean, we have 99.7% of stuff, and moving in and in, it's a smaller percentage within that range.
Yes.
Alright, so in this case, 68.3% of the data is within Z score of -1 to 1. 95.4% of the data is within Z score of -2 to 2.
Why does this work?
99.7% of the data is between -3 and 2.
Wait, Steve.
I think back what I said about last question yesterday about using valid 6 or quadratics. I got into quadratic. It was 5 different types of quadratics, and I will do them. I will do
Now, heights of the 5 starting members of these basketball teams are the same. Oh no, one of them is wrong slightly. are 170, 182, 183, 195, 212. Mean is 190, standard deviation is 15. That's really nice. I didn't have to calculate that. Thanks for giving that to us question. What's the Z-score of the tallest player? Z-score of the tallest player. Here's the shortest player. So we're probably going to use the same formula. Z-score of the tallest player, which, by the way, on your formula sheet, if you look in the statistics category, you have Z-score.
Oh, amazing.
So you can memorize this, but you also So in this case, tallest player is 212. So 212 minus 190 over 15 standard deviation. So we end up with a Z-score of 22 over 15. And Z-scores are using decimals. We definitely use decimals for Z-scores. When you look on your Z-score chart, it's all using decimals. So change your fractions to decimals and round them off. It asks us here's 100 here.
1.45.
Awesome. Yep, 22 over 15 is 1.45. Or 1.47 centimeters 100.
Change most of the degree?
What?
Change most of the degree?
It won't matter. Stats. That only matters in trig.
You know what? This is so much.
Still good if it's in degrees, because until you're in math 30-1, you won't need degrees.
I'm gonna ask Myrna how much she's here.
250 centimeters.
I'm going to make her.
What?
That was a good plan.
I like that.
For example, 76 minus 33 is 70. Divided by a random number, that would be the difference.
What's the biggest minus?
That'd be
I'm trying to see how to do it. Because like 1 divided by 2 is 0.5. But what is the sum? 0.5.
No, the
Like in this
difference is
case,
the standard.
1.47. Oh! Okay, so in this case, we took our tallest player, subtracted the mean, divided by standard deviation.
That's not the smallest.
And 170 is the smallest, but 1
It's
by
the.
So in this case, the range went from negative 1.33 Z-scores up to 1.47. That was old. How about this instead? Z-scores can be used to compare data from normal distributions. Yeah, so by converting the distributions to the standard normal distribution, right? So in this case, Tony's midterm marks are shown below, compared to the class mean and standard deviation. So let's figure out how he is relative to his class. Now, if we just look at raw scores, Tony did the best he can. But let's compare to the rest of those people in his class and see how he did. So, let's see. First of all, in math, what's Tony's Z-score in math? We'll call this, I don't know, Z of math. That sounds like reasonable notation? Z of math, we take his mark, X, minus the mean mark, 68, and divide it by the standard deviation of 12. So we have 6 over 12, so he's at 0.5. So he's above the mean. He's a half standard deviation above the mean. Great job.
Yeah.
That's like a few of you. A half standard deviation above the mean. Great job. And how about his Z-score in Chem? 79 minus 73 over 14. So in this case, we have 6 over 14. 6 over 14 is 3 over 7, 0.42. And how about his Z-Phys? So that's 68 minus 66 over 11. So which one was he best compared to his friends?
Because of you, Mr. Boyce, you're teaching.
Thanks. Yeah, Tony was doing so well that he dropped the class. No longer here. Yep.
That's a
Very
mean.
cool.
No, you're not allowed to actually, no.
Everyone in favor?
In favor, say.
It does seem a little bit rude for me to democratize. Let the bathroom. So your benevolent dictator will just say yes.
Thank you.
Oh, what is
Let the
it?
gods decide.
Okay, now what about backwards? So we were just finding Z-scores are all amazing and adapt to this. So what about instead, average mark was 63, standard deviation was 12. The marks were normally distributed and the student's Z-score is 1.5. What was their actual mark? So let's put this formula, Z equals X minus mu over sigma.
which equals 1.15.
Okay, so yeah, let's think what we can sub it. Let's go back to science line and think how we set up the problem with this. Well, do I have Z? Yep, 1.5. Do I have mu? Yep, 63. Do I have sigma? Yep, 12. Do I have X? That's what I want to find. Your X is gone? Can we find it?
How did you hear that? I don't know.
There's sometimes as a teacher you choose to ignore things. But some things are teachers need to ignore, my friends.
Yes.
Oh my god.
It's like hearing good gossip. You want to.
That's right, everyone had to hear.
Oh my god, I got that, I got
So 1.5 equals X minus 63 over 12, and now you just guess.
No.
Yeah, oh, you.
Oh, sorry, yeah, you do the math, good idea.
Oh,
Now we are algebra our way out of this one. So 1.5 times 12 is 18 equals X minus 63. So this brilliant student has scored an 81%.
Genius.
Whoa, they're so good, yay!
Now like.
Wrong spot.
Right.
If you're gonna clap, put your hands up, not that.
How about this? Large shipment of cantaloupes have a mean cantaloupe weight of 2.3. So that's mu.
Yes.
The weight of a particular cantaloupe is 1.7, and that is 1.01 standard deviations below the mean. Oh, interesting. So we don't know the standard deviations, but we know the Z-score. What's the Z-score? Positive or negative?
No, negative.
Negative, below the mean. Okay. All right, try set this up. See if you can work it out. We're looking for sigma. We have everything else. Good morning. He was in my block 1 class, not my block 2. Yeah. No worries.
Equals 2.3.
And by the way, hey, just by looking at this, without doing any math, can you like approximate it? If that's just a tiny bit more than 1 standard deviation below the mean, it's going to be about 0.6, right? Let's do a little more.
Yeah.
Ask near 10, if not near 10. But it better be pretty close to 0.6, because it's about 1 standard deviation below the mean, right? So let's see. Z-score negative 1.01 equals X 1.7 minus mu 2.3 divided by sigma, I don't know.
But then we can still add it top.
Well, yeah, or you can do your standard. This is a proportion, right? Like if you have this over 1, you would know sigma ends up being equal to, basically flip it over and find the top of the other one. So this ends up being sigma is equal to 1.7 minus 2.3 over negative 1.01, or 0.6 over 1.01. Wait, why? Where's the 0 come from? Why is it on?
That's a sigma.
Sigma.
That's sigma.
Oh.
That's sigma.
When you have a setup like this, you can end up just.
Bro, it's got the same thing.
Yeah, so 0.6, you end up with sigma equals 0.59.
Yeah.
So standard deviation is about 0.6, really, really close to how far you apart was, right? And we knew that because it's about 1 standard deviation below the mean. I think this is probably going to be our last example, eh? I think that our listening capacity is taxed. You guys have done really well. This is a tough lesson. I didn't want to cut math up so I didn't do it all together. So let's try one more example together. Marks on a math exam at university were found at a mean of 52, standard deviation of 12. Okay, let's keep track of this. Okay, mu is 52.
Okay, mu equals.
Good. I was reminded to stop mouth breathing. Excellent. And standard deviation, yes, 12. Professor thought the exam was too difficult. Got softly. Oh wait, I didn't know. No. Decided to adjust the original marks by raising the mean to 65. Okay. while reducing the standard deviation to 10 and leaving the z-scores unchanged. Okay. What would be the new mark for a student whose original mark was 34? Now let's just think of what's happening. So this student beforehand had a 34 on an average of 52. Let's think of what happened there. What was the original z-score? Let's say, what was the z-score on the first test for this student? So z-score is equal to mark minus average over standard deviation. So we have negative 18 over 12. Hey, oh, sugar. So the z-score here is equal to negative 1.5.
Yeah.
And what we're saying is she's going to keep the same z-score. So now on this new window, what will her mark be if her z-score stays the same? So now, in the new setting, z-score is negative 1.5. And we want to know what her mark will be. But we have a new mean, 65. And we have a new standard deviation of 10.
Yeah.
So 10 times negative 1.5, x minus that, what do we get? 65 minus 15 ends up being 50. So her new mark is 50%. This teacher, I think, just really liked that student, knew that they weren't going to pass without his help, so changed the marks so they just barely got there. What a nice teacher. How wonderful, how lovely. Okay, that is a lot of me blabbing, which has left you with a decent amount of time still to work. You have 17 minutes of homework time, and for today, you have been assigned, let's see what we wrote down, I think I did minimize it a little bit. Everything except 10.
Oh,
Yeah,
That's so weird.
yeah, that's not so reduced.
Yeah.
Yeah.
11 hours. Is it? Probably. What time is it? It's like 11. Yes. Yes.
I will have 2 minutes.
Yes.
How about you stop this mammoth recording?
12, 1, 2, 3.